Welcome to episode 68 of the Energy Balance Podcast, where we teach you how to live without constant hunger and cravings, fatigue, brain fog, poor sleep, and other low energy symptoms by maximizing your cellular energy. I'm Jay Feldman. I'm a health coach and independent health researcher, and joining me again today is my good friend Mike Fave. Mike and I have been studying health and nutrition together for a long time now, and Mike also draws on his experiences from working within the healthcare industry. Today's episode is part 6 of our series discussing non-alcoholic fatty liver disease, where in today's episode we'll be talking about oxidative stress, choline deficiencies, and how these relate to exporting liver fat. And throughout this series, we have been discussing the general mechanisms and physiology that are underlying this condition of fatty liver disease. And the reason why we've been spending so much time on this is because the physiology underlying this condition is seen in virtually every other chronic health issue, so it's worth spending some time to dig into. And throughout today's episode, we will be trying to simplify some of the physiology by looking at some graphics. So if you'd like to take a look at those, then I'd recommend you watch this episode on YouTube, but we'll also make sure to explain the graphics verbally as well. And following today's episode, we'll be rounding out this series by discussing what this all means as far as diet, lifestyle, and supplements go, and how we can use this information to resolve or reverse this pathology. In today's episode in particular, we'll be talking about how oxidative stress causes fat to accumulate in the liver. We'll be talking about how a choline and methionine deficiency can contribute to fatty liver. We'll be talking about another mechanism by which PUFA, or the polyunsaturated fats, can cause fatty liver disease. We'll be talking about how folate and vitamin B12 deficiencies can contribute to fatty liver, and we'll also be talking about how the polyunsaturated fats decrease LDL and why this is not beneficial for both our general metabolic health as well as our liver health. To check out the show notes for today's episode, you can head over to jayfeldmanwellness.com/podcast, where you can take a look at the studies and articles and anything else that we reference throughout today's episode. And if you are dealing with any of the symptoms or conditions that we've been discussing throughout this series, whether that is fatty liver or insulin resistance or other related conditions like diabetes or heart disease, or if you're dealing with any other chronic health issues or low energy symptoms like chronic cravings and hunger, low energy or fatigue, chronic pain, brain fog, weight gain, digestive symptoms like bloating or intestinal inflammation, or if you're dealing with other low energy symptoms like poor sleep or insomnia or hormonal imbalances or any other chronic health conditions like autoimmune conditions, then head over to jayfeldmanwellness.com/energy, where you can sign up for a free energy balance mini course where I'll explain how these different symptoms and conditions are really caused by a lack of energy. And I'll also walk you through the main things that you can do from a diet and lifestyle perspective to maximize your cellular energy and resolve these symptoms and conditions. So to sign up for that free energy balance mini course, head over to jayfeldmanwellness.com/energy. And with that, let's get started. All right, so we've talked through all these different factors that have been driving the production of fat in the liver in non-alcoholic fatty liver disease and all of its progressions, and how it starts at inhibited respiration, and then there are all these different factors that can cause that issue and lead to the accumulation of fat. And this has all been on this one side of the equation. So if we're just looking at fat accumulation in the liver, we have fat production, and then we have the release of fat. And it can be helpful to look at sometimes body fat in the same way. I know we've talked about that in a bit in the past as far as, yes, some people are really focused on the burning of fat and the release of fat and lipolysis, but there's also a lot of factors that affect the storage of fat, and so that's a huge part of the equation. So in this case, we've talked about all these processes that come together to drive the production of fat, and then now it's time to look at the things that lead to the release of fat or the export of fat from the liver, because both sides of this equation play a role in fat accumulating in the liver. And as we'll get to, the underlying cause in both the production issues and exportation issues is still relatively the same, but it's helpful to go through some of the details here that are a little bit unique to on this case, the export side, and kind of put those pieces together. So just as a very brief overview, basically the fat that's in our liver gets exported through VLDL, which is the very low density lipoprotein. So I'm going to pull up a graph here, or a diagram here, looking at that. But we've talked, just for reference, we aren't going to dig as much into the whole cholesterol, LDL, HDL side of things. In today's episode, we have talked through cholesterol in the past and why LDL is not the bad quote unquote cholesterol or cholesterol carrier, and HDL is not necessarily the good one. Those things do kind of come into play here in this pathway, but they aren't real central. So we aren't going to be focusing as much on that. I'm going to pull up this graph so we can talk through, in this case, the export of fat through these lipoproteins. So what we have here is the kind of like a complete loop in a way that starts all the way at the production of fat that we already talked about, and then goes from there. So if we're looking on the left side here, we see they talk about glucose, but we've talked a lot about how fructose is a major component here as well. And then the free fatty acids, which are an even greater component, a much greater component, that these are taken up by the liver and lead to the production of fat, of triglycerides. And then you can see that these triglycerides can then be exported in the liver when they are combined with two other things, ApoB, which is a protein, and free cholesterol that's in the liver. And those things all get packaged together into a relatively large particle called VLDL. And that VLDL gets exported from the liver. It enters the bloodstream. They're showing capillaries here where the fat from the VLDL, which is the triglyceride that came from the liver in the first place, that fat gets released into the tissues. As they're talking about free fatty acids getting released into the tissues. And then that VLDL gets, basically as it loses the triglycerides, it becomes what's called IDL. And then as it loses more triglycerides, it becomes LDL. And so this is just talking about different densities that change based on the composition of this VLDL particle or compound, as far as more triglycerides and then fewer triglycerides. So the LDL ends up having a much greater concentration of cholesterol and much less triglyceride because all of that has been dropped off already. And then that LDL can drop off the cholesterol at the tissues. So you see here on the right, the peripheral tissues where the cholesterol is dropped off. And this is mediated by the LDL receptor. Again, this side of the equation or of the pathway is something we talked about more in those cholesterol episodes. And so I will link back to those. It's not quite as relevant here. We might touch on it a little bit, but the more important thing here is all of these factors that come together to create the VLDL and the ability for them to all function properly and then for the VLDL to be released. And that's really what can be dysregulated in fatty liver, and it's shown to be dysregulated in fatty liver and leads to the problem with this other side of the equation of not being able to export fat, so you end up with fat accumulation at the liver.
So with that said, there's two key factors, at least in this scenario, or primary factors in this scenario that can negatively impact the ability of the liver to export the fatty acids and the cholesterol that are being built up inside the liver. The first factor that's a problem is a choline and methionine deficiency. And essentially, we'll get into that, I guess, in more depth. And then the second factor is going to be an excessive oxidative stress a large amounts of oxidation going on inside the liver cells. So just before we get into the choline and methionine deficiency piece, I want to start by looking at what that VLDL actually looks like.
Yeah. So I'm pulling up the graphic, but this is helpful also. So I know I mentioned in that first diagram we had triglycerides, cholesterol, and ApoB that were all needed to create the VLDL particle. But what I didn't mention there, or what wasn't in that diagram, was phosphatidylcholine, which is a major component of the VLDL. And so it does make a huge difference. And that's why, as you mentioned, a deficiency in choline or methionine, which will lead to a choline deficiency, and we'll explain why, that's going to also become an issue that will cause a problem with this pathway. So you can see that here looking at the lipoprotein structure.
Okay, so the lipoprotein structure, what you can see here is this is the apoprotein. This is going to be your apoprotein B100, one of the core lipoproteins that makes up the VLDL. There are other lipoproteins involved, but that's the main one that we're going to talk about here, especially when we get to the oxidation perspective. Then, and attached to this lipoprotein or the apoprotein, the lipoprotein is actually this whole thing altogether. The apoprotein is just the protein by itself. You have the phospholipids that are these little pieces here. They make up this 3D spherical structure. It's basically like if you have an M&M, it's like the chocolate, or a peanut M&M, it's like the chocolate covering around the peanut M&M. And then as you can see, we'll get into the next picture, but before we do that, there are little heads here. They're called a phospholipid, and they have two tails. Now, before we get to that next picture, the interior inside this lipoprotein, the lipoprotein being the apoprotein, and then all the phospholipids, that's these pieces here. You have your cholesterol esters. You have your triglycerides. Another name for a triglyceride is a triglycerol. And you have cholesterol, which can it can be inside the actual coating with the phospholipids, or you can have cholesterol inside the actual lipoprotein. So this is what VLDL is, and the reason why VLDL looks like this is because the fats, the triglycerides, and the cholesterol esters are hydrophobic, meaning they don't react well with water. It's like if you try to mix oil and water, it doesn't mix. So what the body has created was a unique carrying molecule where the phospholipids have their heads are hydrophilic, meaning they can dissolve in water. They can interact with water without necessarily separating to a large extent. They can travel through water. Whereas their tails are hydrophobic or lipophilic, meaning that they repel water, but they are able to mix with fats. So the carrying molecule allows the outer portion to move appropriately in water, and the inner portion to associate appropriately with these fatty substances, your cholesterol esters, your triglycerides, your free cholesterol. And then the lipoproteins have a whole host of signaling effects and structural effects, and inside the apoprotein has a whole bunch of signaling and structural effects inside the entirety of the lipoprotein.
Yeah. Just for context, so this is just the way that our body is exporting fat, right? So this is a fat carrier. It's a lipoprotein, meaning it's a mix of fat and protein, and it's just a way to carry fat. It's a way to export the fat.
Yeah,
and that's what it's doing. This is the way that we get the fat out of the liver, which is definitely important if we're producing too much fat in the liver, or even if we're not. It's a distribution mechanism.
Exactly, and it'll become important as we go to this next slide. There we go. And so the phospholipid here is the little head with the two legs. This is the phospholipid up close. And so basically you have the hydrophilic head, like I talked about, the part that associates with water, and then you have the hydrophobic tails. So these are the actual fatty acids. And this becomes important in fatty liver diseases because these cannot be created if you don't have choline. And choline is one of the main components that creates this head. So if you don't have choline, you basically cannot create the phospholipids. And as we looked at with the VLDL particle or molecule, whatever you want to call it, you essentially can't create the phospholipids to build the VLDL. So without choline, you don't get this phospholipid, and then there's no VLDL. So the liver has no export mechanism. Now, methionine becomes important in this as well, because methionine can be converted or is used to create choline in the absence of adequate dietary choline. It can't replace all of your choline needs, but it makes up, I think, between 20 and 30% of the choline needs for the body. So essentially you want to be intaking adequate choline, for example, from eggs, and then also having adequate methionine from protein. And that will allow you to produce enough choline to export the fat from the liver. And this is in different rodent studies and different animal studies, when they feed these animals diets deficient in methionine and choline, the rats develop fatty liver. Now they may not develop NASH, which is non-alcoholic steatohepatitis, which we talked about many times in the past few episodes, and some of the underlying factors causing it, but they will get fatty liver. And it's literally because the liver is unable to export the fats in the VLDL particles. And the other thing that's important to note is that if the VLDL particles don't have the proper amount of phospholipids present in them, they also get taken up. They get like retaken up by the liver. They get because they're not correct. They're not formed appropriately. So it inhibits the entire process of exporting the fats from the liver, and it can basically cause fatty liver in and of itself.
Yeah. So just to summarize here, the choline is an integral part of the phospholipid part of the lipoprotein, which is the thing that is exporting the fat. And so a lack of choline would be a limiting factor that prevents the liver from being able to get rid of fat and transport it elsewhere, and it leads to accumulation. And so it's important to recognize that, and we'll talk later on about how that fits in and whether that means you need to supplement choline or not, or what you should be doing dietarily. But the important piece here is that choline is a requirement, and a lack of choline, as you were saying, will cause malformed VLDL, which will not be able to be exported. It'll be reabsorbed. And if you don't, and as you were saying, most of the phosphatidylcholine that's coming from the choline and that's used in the phospholipids is coming from choline, but some amount of it can also come from methionine. So methionine is an amino acid. It's one of the main amino acids that is found in specifically animal protein, and it can also be used to produce choline. And it also, if you're getting enough methionine, it decreases the degradation or the metabolism of choline into other compounds. So kind of it basically causes a choline sparing effect, and it can make up for a lack of choline by leading to its production. So both of those two components, the choline and methionine, are important for this export process. I mean, the methionine slightly less so. If you had enough choline, then the methionine doesn't matter so much. But if you did not have enough choline, then the methionine can make up for that to an extent and can help to preserve it. So, yeah. And as you said as well, you can very easily, or in the research, they very easily create fatty liver situations by just depleting choline and methionine, just giving a diet that doesn't have those things.
Yep.
So those things are both important to consider when it comes to the export through the VLDL, and then also some other nutrients, specifically the B vitamins, and more specifically B12 and folate, are particularly helpful in the cycling of methionine and conversion to choline. So those can also, deficiencies in those things or lack of sufficiency in those things could also contribute to a lack of choline, which would also cause issues with export.
Yeah. Essentially, all the B vitamins are extremely important because you have the B vitamins here functioning in methylation, which is what the methionine cycle is involved with. And then you also have the energy B vitamins that we talked about before, B3, B1, B2, which are involved directly in energy production and can help to provide carriers for electrons. So the B vitamins in general are really important. We'll get, I guess, that will be something more for solutions, the solutions episode, which will be next. And then I guess we can jump into the oxidative stress component here.
Yeah.
Yeah.
And just to frame it, in some ways it is oxidative stress, and in other ways too, it's also just the ApoB part of it. Because those things go hand in hand, where we'll get into it. But basically that when there's excessive oxidative stress, it inhibits the other piece, or one of the other integral pieces in the creation of VLDL, which is the presence of ApoB, this protein, or ApoB 100.
Yep. So the first part and the first factor, we don't have adequate amounts of, we can't make adequate phospholipids because we don't have choline. Mm-hmm. And now in the second piece here, the next problem that can happen with the VLDL production, which exports fats out of the liver, is a lack or a destruction or an impairing of proper ApoB production. Mm-hmm. And this is something that occurs directly when you have high amounts of oxidative stress inside or at the liver. at the
Mhm.
hepatocyte. And essentially what happens is the oxidative stress and the ApoB is built inside the endoplasmic reticulum of the cell. When you have high amounts of oxidative stress there, particularly from polyunsaturated fats, especially the omega-3 fatty acids, the ApoB protein is unable to form appropriately. And then therefore the VLDL particle is unable to form appropriately. And the reason why the ApoB forms inappropriately is because of the high amount of oxidative stress or peroxidative damage going on inside the ER from these fatty acids.
Mhm.
So, and I guess I'll let you get into it, but this is usually considered a good thing by like mainstream medicine and whatnot.
Yeah. So, and that kind of gets to what we were talking about earlier, where when we're looking at cholesterol and these lipoproteins, LDL is considered to be a bad guy. VLDL is considered to be a bad guy. HDL is the only one that's considered to be a good guy. And so it's known that the polyunsaturated fats, the omega-6s and omega-3s, will decrease VLDL and LDL and they'll increase HDL. And we talked about why that's not good. This is not necessarily a good thing from the heart health standpoint and the circulatory system standpoint and the vascular health standpoint, as it's made out to be. And I think it's very clear that the polyunsaturated fats specifically are involved in the pathology, in the causing of these cardiovascular issues. And but so because there's this, it's this backwards reasoning that we've talked about before. It's kind of top down, where you have this assumption that saturated fats are bad and PUFA are good. And so you look at all the things that they do through that lens. And so if saturated fat increases LDL and PUFA decreases LDL, then LDL must be a bad thing. And if saturated fats decrease HDL and PUFA increases HDL, then HDL must be a good thing, because we already know saturated fat is bad and PUFA is good. We're already operating on that assumption. And by we, I mean the research that is looking at heart health. And the same thing happens with fatty liver. So then they make this assumption that anything that the polyunsaturated fats are doing, and through any mechanism, it must be a good thing. But when you actually look at these mechanisms, I think it's pretty clear that this is not something that you want to be encouraging. And it also leads to the development of fatty liver and the progression of fatty liver toward NASH. So
I was going to say it also goes the other way too, where there's an already like the generally understood or consensus is that LDL and VLDL is not good and
right.
HDL is good. So you want so if something is raising LDL or decreasing LDL and raising HDL, then it must be good.
Right.
And so it's like kind of going in both of those directions. And
Yep.
the one thing is that like when you look at just for brief physiology with LDL and HDL, the difference between the particles to a large extent is that not only their composition, so the LDL is taking the fats and cholesterol that the liver is exporting, whether that's coming in from diet, whether it's coming in from what the liver just created, and bringing them to the tissues. Whereas HDL is usually less heavy on the triglycerides or the fats and has a higher amount of cholesterol esters, and it's taking those cholesterol esters back from the cells and bringing them to the liver. So what you're really seeing is LDL and VLDL, IDL, and LDL. You can consider them kind of in the same category. They're all taking the fats from the liver and bringing it to the tissues, whereas HDL is taking the cholesterol esters to a large extent from the tissues and bringing it back to the liver. So that's the major difference. And the idea that they have around this stuff is that, well, in all these pathologic states, LDL is elevated. You have it's a bad lipid profile, that you have too much LDL and you don't have enough HDL. And a lot of this is based on association. And there are some causative animal models, but there's some nuances to how those studies are conducted and what's actually going on in those individual states. So there's these assumptions on both sides. Well, PUFA is good and LDL is bad, while HDL is good. So if anything raises LDL and lowers HDL, then it must be good as well. Mm-hmm. And so it gets into more depth than that, right? Because just off the bat, like if you're taking in fats or you're taking in cholesterol, you would want your liver to be sending those to the tissues. That's part of the point. That's the point of the system, is to take out the fats and send them to the tissues. And then Yeah, so there's more to the situation, and we covered some of those things, whether that was endotoxin and whatnot. But you can dig into we'll dig into this other piece now.
Yeah. And so you had prefaced this piece of things by saying that oxidative stress damages the ApoB and leads to its degradation, so it's not able to be used to create this VLDL. And they call this process, they give it this semi-long name that sounds confusing, but it's post-ER pre-secretory proteolysis or proteolysis. And so this, you had mentioned that the ApoB protein is created or released from the endoplasmic reticulum. So they're saying that after it's released from the endoplasmic reticulum, it is then degraded. And so it is not able to be secreted and used in the VLDL. And this is a process that's triggered by oxidative stress. And they recognize that this is the mechanism through which polyunsaturated fats, including both the omega-3s and omega-6s, decrease VLDL and therefore LDL. So, and this, again, this is not, this is not controversial. This is the mechanism that they cite for saying that the polyunsaturated fats create oxidative stress in the liver, and this degrades this pathway of being able to export liver fat. And as we'll get to in a second, this actually contributes to fatty liver and worse. And yet they're saying that this, and this is recognized as the way that these polyunsaturated fats decrease LDL. And, it kind of goes back to all these things that we've talked about in the past, as far as just looking at some end result and not considering how you get there and the problems with that, whether it's, it leads to all of these forms of kind of, of reductionism, this idea that high cholesterol leads to heart disease, the idea that high blood sugar causes insulin resistance and diabetes, or that high amounts of carbohydrate intake or even high amounts of insulin, as opposed to recognizing the underlying issues that are going on. And same thing happens in fatty liver as well. And yeah, you see it in virtually every aspect of these things. And we've talked about in terms of weight loss too. There's a lot of ways that you can create weight loss, and a lot of them are not healthy.
Yeah. You could cut off your arm, you'll lose a couple pounds.
Right. You can get a severe infection. You can get some sort of severe chronic illness. You can diet really hard, barely eat any calories. You can fast. You can, try to run a marathon. These are all things that tend to be extremely stressful and will lead to weight loss. And if you're just looking at that end parameter, they look to be very successful. So instead, when you consider how the polyunsaturated fats are causing this decrease in LDL, it's caused by oxidative stress. And they've found that you can actually prevent the decrease in VLDL and LDL by adding in vitamin E, which is a known antioxidant, among other things, a very protective factor, which is another way. And we know that, so a couple things here. One, we know that PUFA deplete vitamin E, which again makes sense because they're causing oxidative stress, causing the depletion of vitamin E. But it's also interesting to consider that, there are these things that are assumed to be good and bad, LDL, HDL. And I think from even the mainstream, I'm sure they would say that vitamin E is a good thing. And so if there's this direct opposing effect between vitamin E and PUFA on the LDL situation, on the side of LDL, that tends to, that's also an indication that this is not a good thing to be doing, deplete or impairing this VLDL secretion. So anyway, so using vitamin E is one way that they prevent this from happening. And then another way is by chelating iron. So they use some compound to bind with and get rid of iron, which we've talked about how iron is kind of like PUFA in that it's an amplifier of inflammation and of lipid peroxidation. It's very susceptible to becoming oxidized and then passing that oxidation on, and amplifies that sort of damage. And so if you get rid of iron or add vitamin E, then PUFA does not decrease VLDL secretion. It does not decrease LDL, which is why they're saying that it's a good thing. And this is protective in the case of fatty liver, meaning the chelation of iron or the using of vitamin E.
Well, not even in this study, like in other situations, there's some rodent models or animal models where they protect the liver with the antioxidant effects of vitamin E. And I think there was even one study that Georgie posted at one point in time, which was using testosterone and vitamin E to help to minimize the oxidative stress at the liver and decrease fatty liver. So it's like, the other thing I just want to point out really quick here is that the switch from from just regular NAFLD, non-alcoholic fatty liver, to non-alcoholic steatohepatitis is increased oxidative stress at the cell. So it's like we're lowering your lipid profile while increasing your oxidative stress at the liver, but that doesn't do anything for your. But it also, it just turns NAFLD to NASH.
Yeah. Yeah. And you see that. And so there was one study where they were looking at slight overfeeding, 17% above normal calories, quote unquote. And they looked at all different levels of PUFA, of corn oil in the diet, and found that the low PUFA overfeeding did not cause that contribution to NASH, or the progression to NASH. They just had fatty liver. But when they gave them a lot of corn oil, a high percentage of PUFA, and specifically in this case, the omega-6s, that increased the progression toward NASH. And again, through that same mechanism that increased oxidative stress and lipid peroxidation. And this is just seen very clearly. So there's another situation where they've looked at this, where they took rats on a methionine and choline deficient diet, meaning that they are going to have fat accumulation in the liver. We talked about how that's a really reliable way to create that situation. And they looked at low fat diets and then high fat diets, and high fat diets that were high in PUFA, and high fat diets that were high in saturated fats. And so what they found was that, and this is a quote, they say all modified fat MCD formulas, this is MCD meaning methionine and choline deficient, caused identical degrees of hepatic steatosis, that's the fatty liver, and resulted in a similar distribution of fat within individual hepatic lipid compartments. That's just saying that all the diets, because they were deficient in methionine and choline, caused fatty liver. And they said that the fatty acid composition of hepatic lipids, however, reflected the fat composition of the diet. So this is just saying that depending on what composition of fats they ate, that was reflected in the fats in the liver, which is an important thing to note, and something that sometimes people will argue about is, just because I eat polyunsaturated fats, does that mean they're actually going to be incorporated into the structure? Does that mean I'm actually going to be storing them? The answer would be yes to those things. And so then they say that mice fed a PUFA-rich MCD formula showed extensive hepatic lipid peroxidation, induction of pro-inflammatory genes, and histologic inflammation. When PUFAs were substituted with more saturated fats, lipid peroxidation, pro-inflammatory gene induction, and hepatic inflammation all declined significantly.
Yeah. What essentially you're seeing here is it's similar to what we talked about with some of the alcohol studies as well, where the saturated fat led to increased liver fat, but it didn't progress the situation into actual NASH, which is really the real pathology, the real significant pathology is NASH, where you have the actual inflammation in the liver eventually leading to fibrosis and also apoptosis of the cells. Whereas when you just have the liver saying, all right, well, we don't have enough methionine and choline to make phospholipids, so we're just going to have to store this fat in this compartment for this period of time until we can, figure it out down the line. So that's kind of what you're seeing here. The problem is when you're storing the saturated fats, you're not, or even the monounsaturated fats, because I'm sure some of the saturated fats were converted into monounsaturated fats through SCD1, like we talked about previously. The monounsaturated and saturated fats aren't really toxic. They're just sitting there inside the liver cell. They're not peroxidizing, not causing any issues. Whereas the polyunsaturated fats, it's like, you're storing fireworks inside your cell. And it's like, if you have any degree of inflammation, which is likely to happen in these overfeeding states or in these nutrient deficiency diets, it's like now you're lighting the fireworks, and now you're having explosions inside that compartment of the cell, and then the cells are getting inflamed, and then leading to the NASH profile, which is the histological changes they talk about are usually fibrosis, where the actual liver cells die, and then what's replaced are fibroblasts come in and just lay down collagen. So you don't actually have functional hepatocytes anymore. And that's really the problem that you see when the non-alcoholic steatohepatitis moves to cirrhosis, is you severely depleted the number of hepatocytes that you have and have replaced them with the collagen tissue, the non-functional tissue to a large extent. And it's just because you basically blew up the hepatocytes with excessive amounts of oxidative stress. So yeah, it's the other thing I wanted to touch on really quickly was that having enough iron is important because iron has antioxidant functions not directly by itself, but by being cofactors in different enzymes, whether those are some of the glutathione enzymes or some of the other antioxidant enzymes, catalase, whatever that is, that degrade some of the reactive oxygen species. However, in excessive amounts, with excessive amounts of iron, if iron gets exposed to any degree of the polyunsaturated fatty acids in an environment where you are literally having a controlled combustion, which is what our cells do for producing energy, you're just opening yourself up to directly oxidize those, peroxidize those fats with the combination of the iron. And so I don't want people to think that you need iron in the dirt. But the point is like any type of iron overload state. And you can see this with people with hemochromatosis, which is hereditary iron storage issue where they just store way too much iron. They're open to a whole host of oxidative stress because they hold way too much iron in the body. So it's an amount type of thing. You need the right amount, but if you have too much, it's definitely a problem, especially if you're in an inflammatory state. And that's also why you see in inflammatory states people developing anemia. Because the body basically takes all the free iron or the iron that's available and shoves it into a protein to shelter it from reaching everything else. It like packages it in the protein's called ferritin. So it's not about decimating your iron, but it's about lowering your oxidative stress and making sure you have just the right amount. Yeah.
Yeah. And making sure it's being used properly. And there are cofactors there that are important. Copper is a huge one. So that can be another major factor. If you're not getting enough copper, that can lead to a lot of those oxidation issues with iron as well. But anyway, so circling back to that study, they were using a corn oil diet, but I also wanted to highlight that they were comparing with the low fat diet. So there's this diagram that they have, this graph. And so they're looking at T-bars, which is an indication of lipid peroxidation. And they've got the they've got the control, which had no lipid peroxidation. And then they've got these are all the methionine and choline deficient diets. They've got the corn oil, low fat, tallow, and coconut oil. And so they found actually that there was by far the most lipid peroxidation on the corn oil diet, which is to be expected. But then they actually found that the low fat diet had more lipid peroxidation than the tallow or the coconut oil, which I just wanted to highlight that we were talking in the last episode about the protective effects of saturated fat. And so here you're seeing that, right? You're seeing a directly protective effect from ingesting these saturated fats, even in a state of fatty liver compared to having low fat. So that was even better than low fat. And then of course, much better than the polyunsaturated fats. So again, we're just seeing very clearly here that the PUFA are contributing to that progression, to that pathology from just a pure fatty liver, which here they induced by decreasing the export of, or basically completely impairing the export of the fat from the liver by depleting methionine and choline. And then when that happens, when you're in a state where you're accumulating fat in the liver, the polyunsaturated fats drive it toward inflammation, peroxidation, and the pathology that they were describing that leads to NASH and then cirrhosis, which is the fibrotic state even farther, and cancer and all of those other products of inflammation in this fatty liver state.
Yeah. Yeah. So, and the other thing I want to point out here, just on this graph before you take it away, is that if you look at so I want to point out two things. First of all, the control diet, I don't know if you said this, I might have missed it, but the control is different than the low fat in the sense that the control had adequate amounts of methionine and choline, whereas all the other diets didn't have adequate amounts of choline and methionine. So the reason you're not seeing the oxidative stress in the control diet is because the control diet has enough methionine and choline to eliminate the excess amounts of fatty acids. So what's the saying that having adequate amounts of methionine and choline is extremely important to processing fats at the liver. That's what it's showing, because we don't even know we could look in the study what the control diet is, but probably some standard diet. It's not necessarily super important for the conversation, but I doubt that they were giving the control diet tallow and coconut oil or anything like that. It was probably some mix of soybean oil or something like that. And then the other thing I want to point out is that the saturated fats not only lowered the lipid peroxidation, but they also maintained the reduced glutathione. So the glutathione is something that the body uses as an antioxidant. It's one of the major antioxidants.
Mm-hmm.
So what the combination of those two things is showing that the saturated fats just weren't peroxidizing. So there was no need to, or my estimation of it is that the saturated fats just weren't peroxidizing. They weren't causing the liver to need to use its glutathione reserves to basically quench the damage from the peroxidized fats. So that's something that's also, I think, really important to look at. And you see that the tallow and coconut oils still outperformed the low fat diet. So not only did it have less oxidative stress, it also had more reduced glutathione. They could be from the same causes, but they could also be, if it was a refined versus a virgin coconut oil, you could see some effects there. I don't know the offhand what the specific diet was, but yeah, that's I think that's just important to point out. So because when you put it all together, it's like, imagine you had enough methionine and enough choline, and then your fatty acids in your diet were beef tallow and coconut oil. That would severely change the profile of the situation, right? You can have a synergistic effect because not only can you export the fats that you have going on, but if you do have any storage of those fats, they're not liable to peroxidize in the tissues and cause damage.
Yeah. Yeah, exactly.
So, and the other, I guess one more quick thing is that the PUFA here isn't depleting the methionine and choline. The methionine and choline is deficient, and the PUFA in general, this was another study, the PUFA basically impaired the liver's ability to export the fats that it had. So even on a diet where you have adequate amounts of methionine and choline, the polyunsaturated fatty acids can impair your ability to export that methionine and choline as the VLDL, as the IDL, to get it to the tissues.
Mm-hmm.
And so while some people can say, okay, well, now I'll have less LDL. And so if I have any risk factors, I have a lot of inflammation, maybe that LDL will get oxidized when it's being transported. And it's like, okay, so that's all right because now I have less LDL. Well, there's something that's really important to keep in mind is that the thyroid hormone, active thyroid hormone T3, uses LDL to produce steroid hormones at the cell's mitochondria, at your peripheral cell's mitochondria. So when you deplete LDL because you have oxidative stress of the liver with polyunsaturated fatty acids, and you don't have that LDL being exported to the tissues, you're creating a deficiency at the tissues of, or possibly creating a deficiency at the tissues of necessary cholesterol that your tissues would use to produce steroid hormones like testosterone, like progesterone, cortisol, depending on what's needed. So that like deranging that pathway is a problem in and of itself because the thyroid hormone will upregulate LDL receptors at the peripheral cells, and it will upregulate the protein that brings cholesterol into the mitochondria. So it has a twofold effect. So do you want to get rid of your LDL by inhibiting your liver's ability to process the LDL appropriately with a polyunsaturated fat or cholesterol, process it appropriately with polyunsaturated fat? Or do you want to optimize your thyroid function and move that cholesterol to your peripheral tissues and have your peripheral tissues convert it into steroid hormones? For me, the latter option makes a lot more sense, especially when you start digging into the research, which is a bit tangential to what we're talking about directly here, but it actually becomes important when you start looking at the effects of testosterone or progesterone or pregnenolone or DHEA or some of these other hormones on fatty liver and the fatty liver state. And if you put this in context of what we talked about with having an elevated glucocorticoid signaling, elevated cortisol signaling, down regulating your steroid hormone production, particularly testosterone, progesterone, your sex steroids, and then also impairing your thyroid axis, like it synergizes with this perfectly. And it's not something that you would want to continue with. And then on top of that, the polyunsaturated fatty acids don't only produce oxidative stress at the liver cells. The polyunsaturated fatty acids can go to the places like the testicles. And we've talked about this study before, where when they fed the animals high amounts of polyunsaturated fatty acids, the oxidative stress inside the testicles damaged the enzyme's ability to produce adequate amounts of hormones, whereas coconut oil was protective. So these are all, I think, really important things to consider. The polyunsaturated fatty acids are deranging at almost every single level. And the next point is like, with that said, of limiting them would be helpful, but also making sure that you're eating a nutrient dense diet.
Yeah, absolutely. And again, there's so many pieces here that all are working together. So we talked about this before in those cholesterol episodes. But so you mentioned that you want to be getting the steroid hormones from cholesterol, and if you're not exporting LDL, you miss out on that. You also miss out on the immune benefits or necessity of cholesterol, and that cholesterol and LDL both basically together, like the fats and the cholesterol, saturated fats, help to protect against endotoxin and are integral in immune function. They have antimicrobial effects. So you're also missing out on that. You basically have immune suppression with these polyunsaturated fats in this way. And you also have it in other ways as well, which we've talked about in the past, how omega-3s create immunosuppression to the point where you won't even react to a foreign organ that's transplanted into you. So that's pretty noteworthy. But so you have this depression in immune function that is a byproduct of not being able to export fats and cholesterol. But the other thing too is, again, looking at these things as protective mechanisms. You mentioned that PUFA will cause oxidation everywhere, not just in the liver. Well, it's also important to consider that the composition of the fats in the LDL and VLDL, and specifically the VLDL more because those have more fats, will also reflect the composition of the diet. And so those will be higher in PUFA. And that means that the VLDL, as it's getting circulated, will be more easily oxidized. And that VLDL, or the oxidized LDL and VLDL, is found in plaque and in lesions in atherosclerosis, in heart disease. And clearly are implicated there. So you can, again, another way here is that we're looking at this impaired release of VLDL from the liver as a protective mechanism, because if you were to take in a lot of PUFA and continuously release it, you probably cause a lot of cardiovascular issues over time as well. You have this trade-off here where it's a protective adaptive mechanism that we don't want to have to use, because you'd be much better off having the immune benefits and steroid benefits and everything from the cholesterol and fats. But if it's high, if you're exporting a lot of PUFA in that way, it's leaving you very susceptible to continued damage.
Do you want to dig into really quick, just like the difference between saturated and polyunsaturated fats briefly on like the lipid profile, even beyond the lack of export of VLDL?
Sure. Yeah. So I'll just preface it by saying that basically, in the same way that you are inhibiting the release of fats and cholesterol in these lipoproteins, or you're also leading to the uptake of them at the liver and not letting them be exported to the tissues. It's yeah. Go ahead.
Yeah. Well, the reason I was bringing that up was because we were talking about it before, and like the consensus that we came to, and I think that you put it like very succinctly and like more articulate than I did when I went through it, was that like when you eat saturated or the polyunsaturated fats, even though the polyunsaturated fats can impair VLDL secretion through oxidative stress, they still can allow the fats to be produced, the LDL to raise LDL cholesterol and whatnot. However, they also upregulate the LDL receptor on the liver, so the liver will take it back in. And the hypothesis that we were talking about is perhaps having the high amounts of linoleic acid and unsaturated fats in the cholesterol that predisposes them to oxidation. So the liver's like, nah, let me take that back.
Yeah, in the lipoproteins. Yeah.
And the lipoproteins, like, oh, we need to take that back. We don't want that circulating to the tissues. Because again, if you put this all in context, what you're seeing is that the VLDL, VLDL, ILDL, LDL are basically just the system by which the body is transporting fats and cholesterol out of the liver. That's literally what it is. That's all that it is. And then the HDL is just taking back cholesterol esters. That's mainly, I think, what is transporting, if I remember correctly, and then bringing it to the liver. So what you're essentially seeing here is just a big cyclical transport system, and then trying to make associations on, trying to gauge causative effects from the associations that occur with the different lipoproteins and whatnot, and then inferring that decreasing the LDL is helpful, even though you're getting oxidative stress in the liver from the polyunsaturated fats. Like, there's a whole bunch of logical steps that are being completely discounted by making these arguments. Like there's a whole bunch of assumptions that have to be challenged about these particular arguments, especially when you look at the overall context. And that's why it's important when we're talking about something like endotoxin, when you say, oh, in the acute phase response and the response to endotoxin, we have this large amount of cholesterol production because it protects against the endotoxin. So is the LDL really the problem? Or is it the endotoxin triggering the LDL? And then if the LDL is getting oxidized in that particular state, is the LDL getting oxidized because LDL oxidizes, or because the endotoxin is triggering an inflammatory state and then you have fats in your LDL that are likely to oxidize? For me, it sounds more likely that the LDLs, we know it has a protective effect. We know it protects against sepsis. We know it protects against endotoxin. We know it protects against viruses. We know it protects against cancer to some extent. So is it being elevated for these pathologies? And then people are eating, your liver's like, okay, we have a pathology, let's increase the LDL. And then people are eating large amounts of unsaturated fat. And then you have an inflammatory state with a supposedly protective particle loaded with unsaturated fat, then leading to, on top of nutrition deficiencies, then leading to damage to the wall, and then the LDL being oxidized, and the wall meaning the arterial walls, and the LDL being oxidized and being like, look, we can't have this stuff floating around, and the immune cells gobbling it up and the liver taking it back and being like, what is this? This is not what I wanted to put out. So that's like, you're seeing that all of that together, I see is like the actual pathology, not, oh, well, in this state, there's this high LDL, so then LDL must be bad. It's more like, why is the LDL elevated in the first place? Can we get to that root cause and then figure out, okay, why is it oxidizing? You can look at all these different studies and you show that there's a decreased oxidation of LDL with incorporation of monounsaturated and saturated fats as opposed to polyunsaturated fats. And then you look at the effects of the polyunsaturated fats and oxidative stress inside the liver and then at the different cells in the body. And it's just like, yeah, it's probably not, number one, it's probably not a good thing to lower LDL, especially through an oxidative stress mechanism at the liver. And it's not good to lower it when the body's raising it for a pathologic state. And then, because the thing is, it's like, then you're not treating the pathology either. If somebody comes to you and they have a fatty liver and they have high lipid profile, and then you just treat them with a statin, it's like, okay, yeah, they're not producing as much cholesterol anymore. And maybe you put them on an extremely like low fat, low carbohydrate diet. And it's like, well, now their energy production is shot. And yeah, you don't have the substrate going in, but you're not fixing the hormonal profile. And you're not dealing with what's causing the fatty liver and the elevations in the lipid profile either. Did you look at if they have a low grade endotoxemia? What's going on with their digestion? Did you look at any nutrient deficiencies? Did you correct those things? No, we threw a statin on top and we said, now your cholesterol profile looks better. Like, that's not an answer. That is a Band-Aid at best that is allowing the process to continue to some extent and possibly making things worse if the LDL is being elevated because of some type of endotoxemia, some type of low grade infection. Now you just have the infective particles going around, you have immune activation. So you're either at best band-aiding something and allowing it to continue on at a lower speed, or at worst amplifying the process in a negative direction. That's why it's more important to understand the whole system overall and not look just at the associations and then try to determine, what is the nuance and how do all these things fit together? How do all the pieces of the puzzle go together? So that's why when we're looking at something where it's like, polyunsaturated fats are good because they lower VLDL secretion through increasing oxidative stress inside the liver cell, and vitamin E and iron chelation are protective, is like, that is not a good thing. There's not in any world where that is a good thing. It doesn't make any sense.
Vitamin E and iron chelation must be bad. That's really the only logical conclusion. You should deplete
vitamin E.
Yes. Yes, you need fish oil for depleting vitamin E.
Exactly. And the thing is fish oil is a pharmaceutical drug now. They prescribe fish oil to lower triglycerides. And so that's partly why they discuss this mechanism in the study. And so it's like, we're going to massively increase the oxidative stress at your liver so that you have lower lipid profile. There you go. You solved your high cholesterol. It's like that is not an intelligent answer, in my opinion. That doesn't describe what's going on at all. Why is your lipid profile elevated in the first place? Why is your liver storing fat? What's your choline status? What's your methionine status? What's going on at your gut? How much polyunsaturated fat are you eating? How much omega-6 are you eating? How much omega-3? All that type of stuff.
Yeah, of course. And you see that driving pathology as well, right? We talked about how, like we've just gone over, how the PUFA will drive this liver pathology in this case. Maybe it does decrease cholesterol. Well, we know it does, like, right? You're decreasing these markers, but you're directly causing this pathology. And you also happen to see, and I think we mentioned this earlier when we were talking about PUFA in the last episode, you see high HDL associated with non-alcoholic fatty liver disease. And so, and along with this too, I know we kind of went over this a bit, but just to further contextualize, I think a good way to think of it is you have this quote unquote toxic PUFA, and when you're introduced to large amounts of it, the body's natural adaptive response is to keep it in the liver and to bring all of the fats into the liver and keep them there, because the liver can handle it, and it also detoxifies polyunsaturated fats through the glucuronidation pathways. So that's probably our best chance of getting rid of PUFA in that way. And so this all makes sense, and we know what happens when the polyunsaturated fats are circulating. We know that they're prone to oxidation and damage, and that's contributing to all sorts of other pathologies. So this is, again, a way to protect the rest of the body from that major insult.
Yeah, and go ahead.
Well, I was just going to say, and fatty liver, and the progression beyond it is the byproduct, basically. And we talked about that, right? We talked about the fatty liver as a protective mechanism, like all of these other pathologies, if you want to think of them that way. But it's just one that we don't want to have to happen. It's one that obviously comes at a cost.
Yeah, and there's a couple things. The other thing is, like, the fatty liver by itself too, and it being a protective mechanism. Just having a fatty liver doesn't cause massive pathology. What happens is you just have, like, they call it globules, or just inside the liver cell, you just have fatty droplets, right? Where the liver is just kind of holding on to it. Maybe it's deficient, whatever. Maybe it's having a processing problem. Maybe it's having an energetic issue, and it's just holding on to the fats because it can't use all this substrate. It's like you're the engine in a car, and I know the car is not a perfect analogy for human metabolism, but if you flood the engine with gasoline, you have problems as well. There's only
Although we talked about how it's not really the flooding as much as it is like an engine problem.
Yeah, but exactly. But it's like, it's not. You have the problem burning it, and then it's like you don't want to flood the engine, so you're going to store it somewhere else. You're kind of like holding it back. That's what's going on. The difference is it's like if you have the car now and the engine's severely messed up, and you have a fire in the engine, and then you're throwing gasoline on it, like, you're going to blow up the engine. And it's the same kind of deal with high amounts of polyunsaturated fatty acids in liver. That's the progression to NASH, non-alcoholic steatohepatitis, is that oxidative stress. Polyunsaturated fatty acids are some of the most likely things to lead to that oxidative stress. High amounts of iron can as well, but usually through interaction with the polyunsaturated fatty acids. So it's like you have some energetic issue going on or you have some issue going on with the engine and its ability to properly burn fuel. And then rather than like storing this maybe less reactive fuel source, now you're storing like straight up like high octane fuel that if you gets any sense of ignition, it oxidizes, it combusts. So that's kind of the difference. And it's about limiting that capability and then figuring out what's going on at the energetic issue. That's, I think, the most important piece, is figuring out, why am I not, if I'm choline and methionine deficient, am I loading my liver up because I can't export enough of the fats and my liver isn't going to oxidize through all this stuff? Or do I have endotoxin? Again, it all comes down to these. I'm repetitive on it, but it all comes down to figuring out those underlying issues. And while we walk through all the pathologies and all the steps and everything, those steps point us still back to the same place.
Yeah. I just wanted to highlight one last thing that in the same way, as far as the pathology goes, and going back to these mechanisms, that in the same way that PUFA are really effective at causing NASH. We talked about that in the last episode. And today we were highlighting more of how PUFA directly can cause just the fatty liver accumulation by impairing the release of fat. In the same way that both of those things are mediated by oxidative stress. And PUFA are really effective at causing oxidative stress. But you can also cause oxidative stress in other ways that will still be amplified by PUFA, but are just triggered by other things. So just wanted to highlight that again. In the same way that inhibited respiration drives a lack of energy and increases oxidative stress, and that causes fat accumulation, that same process will also impair fat clearance through the same mechanisms that we highlighted using PUFA as the driver, right? So PUFA in this case can be the driver that causes the oxidation of ApoB, and that impairs fat clearance. But PUFA aside, if you are on a low carb diet driving oxidative stress, or if you are lacking other B vitamins or magnesium or whatever else that's impairing respiration and driving oxidative stress, or all of the things that we talked about in the past that might drive lactate metabolism, glycolysis to lactate, where you're not able to fully oxidize glucose. And I'll link to those episodes. Any of those things are also going to cause oxidative stress, and those will also lead to the oxidized ApoB, and those will also impair fat clearance. So just wanted to make sure that, again, even when we're talking on the fat clearance side, much like the fat production side, the inhibited respiration for any reason is really going to be the main problem. And then we do just have a couple of, unique things here. One that's not unique is the PUFA, that's really good at impairing respiration and amplifying oxidative stress. But then we also just have a couple of unique things here as far as those nutrients, the choline and methionine. That's really the kind of things to highlight as far as exportation of fat from the liver. But again, anything that's inhibiting energy production is going to be a main feature of this pathology that can cause it, even if you have enough choline and methionine.
Yep. And something else that we touched upon too, that is a great driver of oxidative stress that I didn't think you mentioned, was oxidizing high amounts of fatty acids.
Right. Yeah. Low carb diet. Yeah.
Yeah. Low carb diet. Exactly. Can lead to higher amounts of oxidative stress. And we talked about this because bottleneck complex 1, complex 2 with ubiquinone, ubiquinol, that also can create issues as well.
Yeah.
And then one other quick point I want to touch upon, we touched upon this in other episodes as well, but even for anybody who has any idea or believes that there's these polyunsaturated fatty acids are essential, the amount that are required in the diet is not like what we're seeing in these studies where you're looking at like 20, 30, 40% of calories is omega-6. It's like
even 10%, 5%.
Yeah.
I mean, the requirements we're talking less than 1% of calories.
Yeah, exactly. For both the omega-6 and the omega-3. So you could eat like 1 gram. The other thing is it's almost impossible and on a whole foods diet. If you have 1 egg a day, you have met your omega-6 percentage. If you eat, if you have some shrimp or you have a couple oysters a week, and then you eat grass-fed beef and maybe you eat some vegetables, you're pretty close to meeting, or you have met your omega-3 percentage that you require. So it's like with a lot of these studies, like with the comparison points, like looking at corn oil, like you are severely over the amount that you need.
If they are essential, you're just saying that argument
there's no case for it. Yeah.
Yeah. It doesn't apply. Yeah.
Exactly. So and the reason I bring that up is because the most solid strategy around dealing with polyunsaturated fatty acids from research, from a logical perspective, I guess from our experience as well, would be to minimize them as much as possible in the context of a whole foods diet, and then eat nutrient dense foods and not try to shoot for some arbitrary target that you see set in Chronometer or something like that. The requirements are extremely low, and all the studies that are comparing them are putting like ridiculously high amounts of them in the diet to get an effect. Because if you just put that minimal requirement, you wouldn't see the same, because it's so low. You wouldn't see the same effect, and it'd be very difficult to do.
Mm-hmm. Yeah.
So just want to put that out there, that even if you believe in that, there's no like this. The strategy is still the same.
Right. Yep. Absolutely. All right. That's going to wrap up part 6 of this series. In the next episode, in part 7, we'll be discussing dietary factors that affect non-alcoholic fatty liver disease, as well as the most important dietary changes to make that would improve non-alcoholic fatty liver disease. If you did enjoy today's episode, please leave a like or comment if you're watching on YouTube. And if you're listening elsewhere, please leave a review or 5-star rating on iTunes. All of those things really do a lot to help support the podcast and are very much appreciated. To check out the show notes for today's episode, you can head over to jfeldmanwellness.com/podcast, where you can take a look at the studies and articles and anything else that we reference throughout today's episode. And if you are dealing with any of these symptoms or conditions that we've been discussing throughout this series, whether that is fatty liver or insulin resistance or other related conditions like heart disease or diabetes, or if you're dealing with other chronic health issues like autoimmune conditions or various other low energy symptoms like chronic cravings or hunger, hormonal imbalances, chronic pain or joint pain, fatigue, weight gain, digestive symptoms, brain fog, poor sleep, or any other related low energy symptoms or chronic health issues, then head over to jfeldmanwellness.com/energy, where you can sign up for a free energy balance mini course where I'll explain how these different symptoms and conditions are really caused by a lack of energy, and I'll also walk you through the main things that you can do from a diet and lifestyle perspective to maximize your cellular energy and resolve these symptoms and conditions. So to sign up for that free energy balance mini course, head over to jfeldmanwellness.com/energy. And with that, I'll see you in the next episode.